All right, everybody, welcome back to some educational content. This is the Exam P ACTEX Study Guide Fall 2020, problem set 1. We're going to do problems 4 through 8, I believe, starting with problem 4. So let's get right into it. Let's not waste any time at all. No time wasted. So, an auto insurance company has 10,000 policyholders. Each policyholder is classified as young or old, male or female, and married or single. Of these policyholders, 3,000 are young. So I'm going to go ahead and start making some variables here. We got y equals young, and there's 3,000 of them. So that's the symbol is the bars on the side are the symbol for the size of the set. So these are sets. 4,600 are male. So we have M is male, okay, and the size of M is 4,600. 7,000 are married. I'm going to make C married. C for, I don't know what C means in terms of marriage, but we're not going to use M. So that's 7,000. Okay, and then the policyholders can also be classified as 1320 young males. So young intersect with male is 1320. And 3010 married males. Intersect M, married males, is 3010. And 1,400 young married persons. So young and married. That's 1,400. Finally, 600 of the policyholders are young, married, and male. 600. How many of the company's policyholders are young? Female, which is the complement of male. So let's actually make that male complement. And single, which is the complement of married. That is the question. Okay. Cool. So what I'm going to do here is set up a chart. And you may have seen this before. You set up one variable. So we have married, and we have single, and we have male, and we have female. And you figure out the stuff in between. But, you might say, oh, I can't do that since there's 3 variables. But you actually can. Maybe if you studied something like game theory, you might know something about how you can do this. But it's very simple. You just set it under the guise of one variable. So, there's young and old. Since this is young, the answer is under young. And we also see young pop up a lot in some of the given answers. I'm going to set this under the young category. Okay? That the chart is under the young category, meaning there's a maximum of 3,000 people. How did I get that 3,000? That was this number, remember? Okay. This will make more sense as we go along. So I'm going to make this chart. We got married. Then we have the opposite of that, which is single. And how many married people are there? There's... Oops, sorry. Remember, I just almost made a big mistake. So this is the mistake I want you to look out for when you do this problem. It has to be young and married. So whenever it's in the chart, it's already classified as young. So I'm going to go ahead and do this one for married. Young and married. That's 1320, right? It's right here. Sorry, that's male. I'm full of mistakes today. Young and married, 1,400. 1,400. Remember, it's a C, not a M. So there we go, 1,400. And then young and single would just be the complement of that. So there's a total of 3,000 people, so it's just going to be 3,000 minus 1,400. Since there's either married or there's single people, the rest of the 3,000 people that aren't the 1,400 married will be single, so that's 1,600 single. Okay? Now I'm going to do it for male on this kind of like y-axis here. And then the complement of that is female. So how many young males do we have? That was this 1320 that I almost stole for the wrong variable. So y intersect m equals 1320. And then the female thing, you do the same thing. 3,000 minus 1320, that's 1,680. Am I right? Yeah, I'm right. Cool. So now we can start getting the juicy stuff here. So how can we combine these variables? We can have a young married male right here in this spot. And in fact, we already have young married and male. That's 600, right? So we can go ahead and put that there. Cool. Now I'm going to go this way to solve it, because this is actually the variable we want, is right here in this spot. But you can do the other way too, and that can actually be a way to check. So anyway, 600 married males. So how many single males, young single males, are there? Well, we can use the same trick that we kind of used earlier. There's a total of 1320 males. So that means that 1320 minus 600 will give us the answer of how many young single males there are. And in fact, that is 720. Okay? So then let's go to our answer that we want to find. And we can use this row of single. So there's 1,600 single people, meaning that 1,600 minus 720 should give us the amount of young single females. And that, in fact, is 880. Okay? And you know what? I'm going to go ahead and do this other spot right here so we can check. So how can we check this? Well, we can see that there's 1,400 married people, and 600 of them are male, so 1,400 minus 600 should give us the amount of young married females, which is 800. Now, does 800 plus 880 equal 1,680? It does. So that means that this is correct. 880 young female single persons. And that is D. Boom, we got that one squared up. Let's move on to the next one. So number 5. The probability that a visit to a primary care physician's PCP office results in neither lab work nor referral to a specialist is 35%. Of those coming to a PCP's office, 30% are referred to specialists, and 40% require lab work. Determine the probability that a visit to a PCP's office results in both lab work and referral to a specialist. Okay. So let's go ahead and set up our variables here, okay? So we have lab work. Let's call it L. So the probability of lab work is 40%, okay? And those being referred to specialists, let's call that, let's call that R for referred to specialists, is 30%. And then those that visit and result in neither lab work nor referral, which is the intersection of their complements, that is 35%, right? So we can actually make this a Venn diagram. Let's do that. Okay, so I went ahead and drew this. This is all we know here. So the lab is 0.40, the referral is 0.30, and outside of both of the Venn diagrams, we have 0.35, which is the intersection of their complements, or neither a referral or a lab happening. So this is kind of similar to another problem where we can find the area inside of the union of referral and lab, which is this yellow highlighted part again. So let's go ahead and do that. And how do we do that? Well, we just take 1, because remember this whole box is equal to 1, minus 0.35, and that will give us 0.65. Remember, we're trying to determine the probability that a visit to a PCP's office results in both lab work and referral to a specialist. Oops. So that's this point right here, right? So now that we know this area of the union of the two sets, we can just use the formula for the union to pretty much figure out the intersection. So that's going to be the probability of L plus the probability of R equal to, and then minus, because remember when we add these two together, we're adding the middle twice. So we want to subtract the intersection of L and R. And we know most of these. So we know this is 0.65. We know this is 0.4. And we know this is 0.30. We know this. We don't know this. We're trying to find it. So then let's just solve for that. So this will be 0.7. We can do 0.65 minus 0.7. And that's going to be negative 0.05. I'm going to go ahead and skip a couple steps here. Since we have a negative here, it's going to be positive on the left side. And that's the answer, 0.05. The way you can check this if you want, you can put it right here, and then you can see, oh, this is going to be 0.25 then right here, and this will be 0.35. And that does add up, so that's going to be 0.40 for the lab. That's going to be 0.30 for the lab. So it works. And there's your answer. Okay, moving on to number 6 here. You are given that the probability of A union B equals 0.7, and the probability of A union B complement equals 0.9. And we are asked to determine the probability of A. So I think the best way to do this is to draw a Venn diagram. I'm going to use colors for this one because I want to. We're going to make this one B, make this one A. Cool. Now, we know that probability of A union B equals 0.7. And so that is the union. So we've been highlighting before in other problems. So this orange part that I'm going to highlight totals to be 0.7. All right? And then we also are given that the probability of A union B complement is 0.9. So then it's going to have A, right? And then everything outside of B. So then just the rest of this box here. All right, so I'm not really good at coloring in the lines here, but you get the point. We can find this data right here, right? It's pretty obvious. All you have to do is just realize, again, that this is 1, this whole box, and the pink part or purple part, whatever, covers all of it except this portion right here. So we can just take 1 minus the probability of A union B complement, which is equal to 1 minus 0.9, giving us that this is equal to 0.1. Okay? Now we know the probability of A union B is 0.7. That's this orange part right here. You can't really see it because it's kind of blended here, but we take the union, this whole portion right here, the two circles together, and then you just subtract 0.1. And that's just going to give you probability of A, which is what we want. So it's pretty simple. So it's just going to be 0.7 minus 0.1, which is equal to 0.6. And that's your answer, 0.6. Okay, we're back for number 7. A survey of a group's viewing habits over the last year revealed the following information. 28% watched gymnastics, 29% watched baseball, 19% watched soccer, 14% watched gymnastics and baseball, 12% watched baseball and soccer, 10% watched gymnastics and soccer, 8% watched all 3 sports. Calculate the percentage of the group that watched none of the 3 sports during the last year. Okay, so how do we do this one? Well, first off, let's just make the variable name. So we're going to have G for gymnastics, S for soccer, and what's the last one? B for baseball. All right, pretty straightforward. And so we can kind of understand what these are. So this is probability of G, this is probability of B, this is probability of S, this is probability of G intersect B, this is probability of B intersect S, this is probability of G intersect S, this is probability of G intersect S intersect B. Okay? So we can make a Venn diagram. I'm going to do that really quick, just so we can visualize it. You don't need it, but I always find it a little useful. Okay, say this is B, say this is G, and say this is S. Now, what we want to find is basically the area of everything outside of the Venn diagram itself. So, the complement of everything. What we want is G complement intersect B complement intersect S complement, right? We wouldn't want the union because the union of all these complements would basically be the entire rectangle, including the stuff in the Venn diagram. So we just want the stuff out here, right? So how can we find that? Well, by something called De Morgan's law. Don't be confused by that vocabulary term. But by De Morgan's law, we can say that this is equal to 1 minus the probability of G union B union S. And you can just visualize that, right? Because we want everything outside of this union, right? We want, here, I'll kind of highlight a little bit. We want everything out here that's not in the circles. So it makes sense that 1 minus the union of everything would give us the intersection of the complements. But how can we find this? Well, look at the information we're given. We're basically given every single data point in here. The only problem is that sometimes they are repeated. So the probability of G already contains the intersection of G and B, and the intersection of G and S, and the intersection of GS and B, right? So to find the union, you just kind of have to use the union formula, but on a larger scale. So let's go ahead and calculate the union of everything. S. So it'll be probability of B plus probability of G, just adding up all of these, probability S. And then we subtract all the intersection points, right? Probability of G intersect B. And we can put these in parentheses and add them together. But we're subtracting all of them. Probability B intersect S plus probability of G intersect S. Okay? And then we subtract the very middle point, which is the intersection of everything. Probability B intersect G intersect S. Okay? So we can just plug those data points in. Probability B is 29%, plus probability G is 0.28. I really put these out of order. It's kind of confusing. Soccer is 0.19 minus, let's see, gymnastics and baseball, that's 0.14, plus 0.12, plus 0.10, and then finally minus 0.08 for the very middle intersection. And we add those all up and subtract them as well, and that turns out to be 0.48. Okay, and so then we go back up here to this equation, and we just take 1 minus 0.48 to find this yellow portion here, and we get 0.52. And that's the answer. And that is D. Okay, on to number 8. This one's a little hard. I would say it's probably the hardest one, so far at least. So, under an insurance policy, a maximum of 5 claims may be filed per year by a policyholder. Let Pn be the probability that a policyholder files n claims during a given year, where n equals 0, 1, 2, 3, 4, 5. An actuary makes the following observations. Pn is greater than or equal to Pn plus 1 for n equals 0, 1, 2, 3, 4. The difference between Pn and Pn plus 1 is the same for n equals 0, 1, 2, 3, 4. Exactly 40% of policyholders file fewer than 2 claims during a given year. Calculate the probability that a random policyholder will file more than 3 claims during a given year. Okay, how I want to start this is by kind of putting this given information into equations that we can kind of understand and work with. So the first thing that's pretty obvious is that P0 plus P1 plus yada yada, all the P's, summing all of them together should give us 1, right? That's just how probabilities work. For this second point, we can figure out that P1 minus P0, so the difference between Pn and Pn plus 1 is the same as P2 minus P1, P3 minus P2, P4 minus P3, and finally P5 minus P4. Okay, that's basically what the second point is saying here. But it's easier kind of to write it down. And then the third point, here I'll label this as 2. And then the third point is saying that exactly 40% of policyholders file fewer than 2 claims during a given year. So that means fewer than 2 claims is 1 and 0. That means that the probability of them filing 0 claims plus the probability of them filing 1 claim is 0.4. Okay. So what can we do with this information to figure out the probability the random policyholder will file more than 3 claims? And more than 3 is just P5 and P4. That's kind of all we need to find here and figure out. The important thing kind of to realize is that these differences are all the same. So we can kind of just use that as a variable. So I'm just going to set this as t, this difference that's present in all of the probabilities here. And so the way you can kind of rewrite this is based upon P0 and T, right? Because P0 obviously equals P0, but then P1 equals P0 plus T. Okay, you see where I'm going with this? And then P2 equals P0 plus 2T. And then P3 equals P0 plus 3T, and so on, right? And so then we can use this equation here that we came up with and add them all together and set it equal to 1. So you make a new equation with T and P0 instead of all these separate probabilities. So it's kind of simplifying the equation to things that you can kind of solve for. So then let's do that. So we have P0 plus T plus P0 plus 2T plus P0 plus 3T. I'm just going to keep going. Cool. And this is just equal to 1, right? So then let's just add up this left side. It's going to be 6PO plus 15T equals 1. Okay? So this is one equation here. Now, we can use this equation. I'll change it over so you see how I'm pointing out. We can use this equation to figure out a second equation to solve for T and P0. Because once we have P0 and T, we can solve for P5 and P4. We can pretty much get whatever probability we want based upon those variables. Okay? So let's get that second equation. So P0 plus P1 equals P0 plus P0 plus T, which is equal to 2P0 plus T. And this is 0.4, as we figured out earlier. So this is our second equation. Okay, so we have a system of equations, basically, that we can set up here. So I'm going to solve for T with this equation. So T should equal 0.4 minus 2P0. And then I'm going to substitute this back in to the second equation. So let's number these equations. So that's 1 and that's 2. So substitute into 2. So 6P0 plus 15 times 0.4 minus 2P0 equals 1. Okay. And so we can kind of add these together. P0 equals 5 over 24. I'm not going to do all the algebra here. So there's our first variable. And then we can substitute it back in. So substitute this into 1 is what I'm going to do. PO into 1, and you get 2 times 5 over 24 plus T equals 0.4. And you solve for T, and you get that it's equal to minus 1 over 60. Now that we have these two, we can find P4 and P5. And when we add those together, it should be our answer, right? Because it's more than 3 claims during a given year. So let's go ahead and do that. Probability of more than 3 claims equals P4 plus P5, which is equal to P0 plus 4T plus P0 plus 5T. And we substitute these variables in, and we should end up with 0.27. And that is C. So there you have it, number 8.